number 15. This is going to be on the complex numbers. Part 2. Okay, so on Monday we did part 1, and we learned all about complex numbers, what they are. We learned some interesting facts about them. You can add them, you can subtract them, you can multiply and divide them. We didn't talk much about what the uses of complex numbers are for, but we're going to get into that a little bit today. So last time we talked about complex numbers, we learned a couple facts about them, right? First of all, we learned that the complex numbers have a real part and an imaginary part. So for any complex number, usually when we talk about complex numbers, we use the symbol Z. And what we're going to say is Z belongs to the set of all complex numbers. So the Z right there, that's a complex number. This symbol right here stands for belongs to. And this capital C right here, this is the set of complex numbers. So we learned last week that there were these things called number sets, and every single number set is represented by a capital letter. And for the complex numbers, we're going to use the letter C to stand for complex numbers. So basically all we're saying here is that there exists a complex number Z that belongs to the set of all complex numbers. Okay? So we know that Z can always be written as A plus BI. A plus BI, where A and B are real numbers, right? A and B are going to be real numbers. And I is actually not a real number. It's a complex number. It's going to be equal to the square root of -1. So that's what I is. I is the imaginary unit. I is the imaginary unit. And that's pretty much what I stands for. I is going to be equal to the square root of -1. So one of the reasons why we use complex numbers in math is because we want to be able to take square roots of negative numbers. And you'll see that a little bit later today. Now, as a result, we know that I is equal to the square root of -1. So we can also say that I squared is equal to -1, right? Because if we square both sides of this equation, look at what happens. If we square both sides, the I is going to become I squared. And then if we square the right side, notice how the square root symbol just kind of goes away and we're left with -1. So this is a fact that we're going to be using today. I squared is equal to -1. So these two things, they're pretty much the same thing. Okay? Now, we also learned that complex numbers have a real part and an imaginary part. So let's talk about that a little bit now. All complex numbers have a real part and they have an imaginary part. So the way we say that is we say that the real part of Z is A. So A is always going to be the real part. But then we can also say that the imaginary part of Z is B. So B is going to be the imaginary part, while A is the real part. Okay? And we also learned about complex conjugates. So let's talk about those now. So for every single complex number, we have what's known as a complex conjugate. The complex conjugate of z equals a plus bi is z bar. So what I do is I take that symbol z and I write it with a bar over it, and we just call it z bar. So z bar is equal to a minus bi. Okay? So all we're doing here is we're keeping the real part the same, but the imaginary part is going to switch sign. So let me write that down here. The imaginary part switches sign. The imaginary part switches its sign. And that's just because, I give you positive b, you would give me negative b, right? The b is switching its sign from a positive to a negative. But if I was to start off with a negative, a minus bi, you would switch the sign back to a positive for the conjugate. Okay? So here's a fact that we just talked about. Fact. Z bar is equal to z. Okay? So what this is saying is, if you have the complex conjugate of z, and you take the complex conjugate of the conjugate, you'll get z again, right? Because if we started off with a plus bi, and I told you to give me the conjugate, you would switch the sign to a minus bi. And then if I said, hey, switch it back again, you would be right back where we started, at z equals a plus bi. So the conjugate of the conjugate is z. And that's the way I like to think about it, okay? So if you do the conjugate thing twice, you're going to get back to your original z. Okay. So last time, we also learned that we can add complex numbers and we can subtract complex numbers. So let's take a look at that. So we also said that if there were two complex numbers, let's say z1 is a plus bi and z2 is c plus di, then z1 plus z2 is going to give me a plus c plus b plus d I. And when we add complex numbers, what we're really doing is we're putting the real parts together. So a and c are going to be put together right here. And then the imaginary parts, b and d, those are going to be combined together over here. And the I is always going to be on the outside of the parentheses, right? So we have that, but we also have subtraction, right? We can subtract z1 and z2. So we also know that z1 minus z2 is equal to a minus c plus b minus d I. So we can add complex numbers, but we can also subtract complex numbers, right? Now, we also learned that we can multiply them together, right? So let's talk about that. What would z1 times z2 be? Let's do it down here. z1 times z2. So here what we're doing is we have a dot in the middle, and that just means we're multiplying two complex numbers together. So I'm going to have a plus bi over here, and on the right side, I'm going to have c plus di. So I've got two complex numbers. We're multiplying them together. So I could put a dot in the middle, but I'm not, because the parentheses tip you off that we are multiplying. And when I do this, I'm going to do the FOIL method. So we all know that the letters of FOIL mean first, outer, inner, last. So we're going to be following that today. So what are the first two terms? That's what the F stands for, the first two terms. Well, that's going to be A and C. So we multiply those first, and we get A times C. The next thing we're going to do is we're going to look at the outer two terms, because that's what the O stands for. So what are the outer two terms? Well, A is on the outside and DI is on the outside. So I'm going to underline DI. So now we're basically looking at this. These are the outer two terms, right? So we're going to multiply those together. A times DI is ADI. Okay. Then the next thing we're going to do is we're going to choose the inner two terms. That's what this I stands for. So when we do the inner two terms, we're looking at the two terms that are on the inside, BI and C. So I'm going to underline BI and C. And what I'm going to do is I'm going to connect them upwards like this. Okay. Now, what's BI times C? That would be BCI. Notice how I'm always putting the I at the end of all these terms, if there is an I. Okay. So we did our inner. So then the last thing we do is our last two terms, right? That's what the L is going to stand for. L stands for last. So the last two terms are going to be BI and DI, right? Because they're the last two in their parentheses. So I'm going to connect them with a blue pen like this. So now BI and DI, they're going to get multiplied together. Okay? So what's BI times DI? That would be BDI squared. So we have B times D, and notice there are two I's that we're dealing with, so that's why we're going to get I squared. Okay? So now what we can do is we have the two terms in the middle that we can put together. Why are the two terms in the middle able to be put together? It's because they're like terms. Notice how they both end in an I. So what I can do is I can bring down my AC like this. We haven't done anything with the AC yet, but I can put the AD and the BC together. I can add those terms up. And we're going to put those together in a single set of parentheses, and we're going to put I on the outside. So what happens to this BDI squared over here? Well, we learned up here that I squared is equal to -1, right? This I squared up here, we're going to be using that fact today. If I squared is -1, then I know that this I squared can be replaced with a -1. So this is actually going to become a negative BD. Okay? So all I did was I replaced the I squared with a -1. So now what do I have at the very end? Well, the AC comes down, and over here, this is going to turn into a negative BD. So this is going to become a negative BD. And then I add my middle terms. I have AD plus BC in parentheses, and the I is on the outside. Yeah, so that's it. And I have no idea why I use double parentheses. It doesn't require that, but I guess I just wasn't thinking about it. So that is how you multiply complex numbers together. You actually use the FOIL method. Okay, dividing. You can also divide complex numbers. And if you need a little bit of help on that, I did it on my last Zoom meeting. You can look up the recording, but for now, I'm not going to go there. I want to cover 3 more topics before we end today. So division is going to be something that you can look at the last lecture for. Okay? So that is the 4 operations. You can add them, you can subtract them, but you can also multiply and divide them, right? Okay. So now let's talk about something a little bit new. We're going to talk about graphing complex numbers. Graphing complex numbers. And this is actually pretty simple. Okay, so when you graph complex numbers, you're going to have a complex number a plus bi, right? We're always going to have a plus bi. Well, we can say that this is graphed on the complex plane. Okay, so there's something called a complex plane. I'll show you what that looks like in a minute. But the complex plane is going to be, symbolized as a capital C. So it's going to be symbolized as a capital C like that. We can graph them as the point A comma B, or the real part of Z and the imaginary part of Z. Okay, so basically what this means is I give you a complex number a plus bi, and the real part is going to be a, and the imaginary part is going to be b. So what we can do is we can draw a complex plane that looks like this. We're going to have an x-axis, and we're going to have a y-axis. So let me draw those real quick. When we do this, we're going to say that the x-axis is actually going to be the real axis. So over here, I want you to write RE, and RE stands for real. So then over here at the top, let's look at the imaginary axis. So the y-axis is going to be called the imaginary axis. We can label that as IM. Okay? And let's go ahead and draw our little tick marks. We're going to have 3 right here, 3 right here, and we're going to have 3 over here. So 1, 2, 3. Then on the left side, we have 1, 2, 3. Okay. And I'm going to label them as 1, 2, 3. And then on the imaginary axis, we're also going to have 1, 2, 3. Okay. So as you probably already know, this is the XY plane. But since we have a real axis and an imaginary axis, this is going to be called the complex plane. The complex plane C. So I'm going to draw a C off to the side. So all the positive numbers are going to be on the right side, and then all the negative numbers are going to be on the left side. The -1, the -2, and the -3. And then on the imaginary axis, you know that all the positive numbers are going to be on the upward side, and the negative numbers are going to be on the downward side. So this is -1, -2, -3. And the point where the two axes meet is going to be 0, but I'm not going to write that. Okay? So let's say we want to graph the complex number, let's say 3 plus 2i. I want to graph 3 plus 2i. Okay, so how is this going to work? Well, every complex number has a real part, and every complex number has an imaginary part. Here, what would the real part be? The real part would be 3. So this is the real part. The imaginary part is always going to be the number attached to the I. So the imaginary part is going to be 2. So how would we graph this? We would graph it as the point 3, 2. So the real part is always going to go where the x is, and the imaginary part is always going to go where the y is. So how would I graph this? Well, I would just graph it as an ordered pair, right? So the 3 tells me how far to the right to go, and the 2 is going to tell me how far up we go. So this is telling me go to the right 3. So I'm going to go to the right 3, 1, 2, 3. And then the 2 is going to tell me to go up 2. So I'm going to go up 2, and I'm going to draw my point. And I'm going to label this point as Z1, because I'm going to say Z1 is equal to 3 plus 2i. Okay? So that's how we graph complex numbers. And you could leave it like that. Another way that I've seen it done is you can actually draw an arrow from the origin to the point. So I could draw an arrow from the 0, 0 point right here and connect it all the way to my complex dot over here. And I put the arrow at the very end. Okay? And then the last thing we're going to do is we're going to graph Z2. Z2 is going to be -2 minus 3i. That's what we're going to be graphing next. -2 minus 3i. All right, so what would this look like? Well, we always have a real part and we always have an imaginary part. The real part is always going to go where the x coordinate is. So -2 is going to become my real part. That's my x value. And the imaginary part, -3, that's going to become my y value. Okay, so I have the point -2, -3, and I put the dot on the graph where it should go. So the -2 tells me, hey, go to the left 2 first. So I'm going to go left 2, and then the y coordinate is going to tell me how far down or up to go, right? This is saying go down 3. So I'm going to go to the left 2 and down 3. And then my point is going to be right here. And we're going to label it Z2. Okay, that's my dot. Now I'm going to draw a line from the origin to my dot. And I'm going to put the arrow at the very end. There we go. That's going to be my complex number Z2. And that's how you graph complex numbers. Very simple. Okay. The last two things we're going to do today are we're going to be simplifying radicals and we're going to be finding powers of I. Okay? So I'm going to give you guys a minute to copy this down and then we'll move on to the next thing. We're going to be simplifying radical expressions. That's the next thing we're going to be doing. Okay, simplifying radical expressions. So what I mean by this is you're going to have something inside of a radical, and that radical is going to be a square root. Just for our purposes today, it's always going to be a square root. It's never going to be a cube root or anything like that. Okay? So you probably already know that you can take the square root of positive squares. So for example, the square root of 9 would be what? The square root of 9 is 3, right? But what if we have to take the square root of -9? What if we have to find the square root of -9? That's a little bit more difficult, and that's going to involve complex numbers. So whenever we're taking the square root of a negative number, like this -9 right here, we're going to have 3i. 3i. And the reason why the I is coming into play is because of this negative right here. We can always take the negative out as an I, and you'll see that when we go through a couple of these problems. Okay? So let's look at square root of -25. What would this be? Now, I'm taking the square root of a negative number. And whenever we take the square root of a negative number, an I is going to come out. So this wouldn't just be 5, but it would be 5i, right? That negative always comes out of the radical as an I. Okay, let's try another one like that. We're going to do square root of negative 12. So what would that be? Square root of negative 12. What I would do for this one is, since the number under the square root is negative, I would first start off by taking the negative out as an I. That's the very first thing I would do. So I would take the negative out as an I so that the new number under here is positive. So all I did so far was I took the negative out as an I. The next thing I'm going to do is I'm going to take that 12 and I'm going to break it up into 3 and 4, just like I did last time. So this is going to become I times the square root of 3 times 4. And we know that the 4 is a perfect square. So I'm going to underline that. The 4 gets underlined. So now what I can do is I can take the 4 out as a 2, because I know that the square root of 4 is going to be 2. So the 2 is going to come out and it's going to join the I. It's going to join the I on the outside. So now what is the only thing I have left under the radical? It's going to be that 3 that I wasn't able to take out. And then I'm done. So that's how we're going to simplify radical expressions. Whenever you have a negative number under the square root, you can take the negative out as an I first. And then after that, you can break it down like usual. So the next one I want you to try on your own. See if you can find the square root of negative 18. What would that be? And while you're doing that, I'll go ahead and be writing down the next problem. Okay, so were you able to figure it out? The negative 18 is going to become a positive 18, but only if I'm able to take the negative out as an I. So the I is going to come out first. So now that I have the I out, it becomes a positive 18 on the inside. So now what I can do is I can break up the 18 into 9 times 2, like I usually do. So this is going to become I times the square root of 9 times 2. And when I break it up into factors like this, I always underline the perfect square because I know I'm going to be taking that out as something. Okay? So we know that 9 times 2 is 18. 9 is a perfect square. So what's the 9 going to come out as? It's going to come out as the square root of 9, right? And what is that? It's going to be 3. So the 9 is actually going to come out as a 3. And it's going to join the I on the outside, while the 2 remains on the inside. And that's it. Can't do any more. All right, let's look at this one. So when I do problems like this, where I have numbers and variables, I always start off with the numbers first, and then I go from there. So I can take the negative out as an I before I do anything. So the I is going to come out, and it's actually going to change into a positive on the inside. A positive 24, x to the 6, y to the 4, and z cubed. And from here, I can break apart that 24 into 4 times 6, right? So this is actually going to become 4 times 6. Four times 6. And then the variables come after that. So x to the 6th power, y to the 4th power, and z to the 3rd power. Okay, so I underline my 4. I know to underline the 4 because that's a perfect square. And the 4 is actually going to come out as a what? The 4 is going to come out as a 2, right? So it's going to come out as a 2. It's going to join the I on the outside, but the 6 has to stay inside with the variables. The 6 has to stay on the inside with the variables. It doesn't come out yet. Okay, so now what do? I can take the variables out in groups of 2, right? All I'm doing here is I'm dividing the exponents by 2. And I'm seeing how many x's, how many y's, and how many z's can come out. So looking at the x's just for a second, I know that I have 6 x's. That means 6 divided by 2 is 3. So I can take out 3 x's. So I have 2ix cubed. And I'm going to stop there. Then I'm going to move on to the y's, okay? Now we have 4. So what's 4 divided by 2? That would just be 2, right? So I can take out 2 y's. And all the y's get taken out. Now look at the z's. How many z's do I have under here? 3, right? So what's 3 divided by 2? Well, that would be 1 remainder 1. So I know I can take out 1 z, but 1 z has to stay inside, right? I could take out 1 z, but then one of the z's has to stay on the inside with that 6 right here. And I'm done. That's as much as I can take out as possible, right? I can't take out anything else. So that's what the hardest problems are going to look like when you do these radical expressions. Okay? All right. The last thing we're going to talk about before we leave today is the powers of I. So I'm going to get a new sheet of paper, and I'll give you guys a minute to finish this up, and then we'll move on to the last thing. We're going to learn about the powers of I. So when I say powers of I really mean we're taking I, the imaginary number, and we're taking it to different exponents. So we can square I and see what that is. We can cube I and see what that is. And we're going to see what happens as we get to larger and larger exponents. Okay. So let's talk about the powers of I. Let's draw a chart or a list. I think I'm going to do a list first. The first thing we're going to do is we're going to raise I to the 0 power. And that's going to be pretty obvious. And then we're going to have I to the first power, I to the second power, and I to the third power. And then we'll even get to I to the fourth and I to the fifth after that. So we're going to figure out what all these things are. And each one kind of takes a little bit of thinking. So we're going to have to talk about these individually. Okay? So when I say powers of I, I'm talking about exponents, right? I'm talking about exponents. So whenever I say powers, I definitely also mean exponents. Same term. So what's I to the 0 power? Well, we know that anything to the 0 power is going to be 1. So I to the 0 power is actually 1. That's our first answer. So now let's think about what I is when we raise it to the first power, okay? What's I to the first power? Wouldn't that just be the same thing as we started off with, I? So I to the first power is just I, okay? So what's I squared going to be? Do you remember what I squared is? Well, if you forgot what I squared is, I want you to look at this. Remember when we started off today and we said that I squared is -1, right? That's one of those facts that we learned. So I squared is actually going to be -1, okay? So now what's I cubed? Well, all I'm doing here is I'm multiplying by I again. So what's -1 times I? That would be -I. It would be -I. Because what am I doing? I'm taking our previous answer, that -1, and I'm multiplying it by I to get -I. Okay? And then I to the 4th power, we just multiply by I one more time, right? So we have I times I times I times I. And I'll give you a few seconds to get that down. So what we're doing now is we're multiplying I by itself 4 times, and we're seeing what we get. So if I multiply I by itself 4 times, what happens? Well, we know that I times I is going to give me -1, and that's because I squared is -1. So these first two are going to give me -1, and then the last two are the same thing. They're going to give me -1 as well. And then what's -1 times -1? That would just be +1. So I to the 4th power is going to be +1. Okay? And then I to the 5th power, we're multiplying by I again, right? So what's 1 times I? That would just be I again. So now the pattern is starting over again. So what's the pattern? It's basically going to be these first 4. So I'm going to draw a box around I0 to I cubed. I'm going to draw a box from I0 to I cubed. This is the pattern. And the pattern is going to repeat itself down here. Okay? So we start off with 1 and we go to I. We start off with 1 and we go to I. Right? But then we go from I to -1. So I is going to go to -1. Okay? And then -1 goes to -I. -1 goes to -I, right? And then -I goes all the way back to 1 again. So this is going to go all the way back to 1 again. And that's the way the pattern is going to go. It's always going to go 1, I, -1, I, 1, I, -1, I, 1, I, -1, I. It's like a 4 repeating pattern that we have here. So can you fill in these right here? If the pattern repeats itself, what would these be? And then what would these 4 be? I to the 8th, I to the 9th, I to the 10th, I to the 11th. What would these 4 be? Okay. Well, if the pattern repeats itself, like I think it does, then we're going to go from 1 to I, and then from I to -1. So we're going to have -1, and then what comes next after -1? -I, right? So we have -I. And then the pattern repeats itself again because we're going to go all the way back to 1. So 1, I, -1, I. And then the pattern keeps on repeating itself. So how do we use this to use it in practice, right? Like how do we find I to a certain power? Well, let's try this one right here. I want to know what I to the 23rd power is. What's I to the 23rd power? That's what we're going to be looking at next. What happens when we take I to a certain power? And the exponents are going to get bigger and bigger. So that's why we're concentrating on these larger numbers. Okay? So I to the 23rd power. You could just do the pattern over here and keep going until you got to I 23. So you could just do that. What I'm going to do, though, is I'm going to teach you a shortcut. So what I do is I always tell the kids to take that exponent that you have and divide it by 4. Divide it by 4, always. Because what we're doing is we have a 4 repeating pattern, right? we only have 4 possible answers. It could be 1, I, -1, or -I. So if I divide this by 4, what happens? Well, think about it. What's 23 divided by 4? That would be at least 5, right? Because I know that 4 can go into 23 5 times. But what's the remainder going to be? The remainder is going to be what? Isn't there going to be 3 left over when we get done with this? So what I'm going to do is I'm going to say 23 divided by 4, that's going to be 5, remainder 3. And I circle the remainder, so the remainder gets circled. Now, this is going to tell me where I'm supposed to go, right? What I'm going to do now is I'm going to match that remainder up with one of these 4 options right here. So 3 tells me to look at I to the 3. I to the 3rd power is -I. So my answer is going to be -I. -I. And I'm basically getting that from this table right here. So another way you can think about it is you have a remainder. I'm going to call it RE. And you have a answer, ANS. So what we could do is we could say, hey, what's your remainder? If your remainder is 3, then your answer is going to be -I. And we could say the same thing for 0, 1, and 2. So what happens if your remainder is 0? Well, if your remainder is 0, that means you cleanly divided something. You don't have any remainder left. So I look at my table over here, and I know that 0 corresponds to 1. So I'm going to put a 1 over here. Now, what happens if your remainder is 1? Well, looking at the table over here, I see that 1 corresponds to I. So my answer is going to be I, right? If my remainder is 2, what's my answer going to be? Think about it. What if my remainder of 2? What would my answer be? It would be -1, right? -1. So that's what you could also use. You could use a remainder table, but I find that this works just fine. These 4 powers of I right here, because the pattern of 4 repeats itself every single time, right? Let's look at a couple more and then I'll call it a day. What is I to the, I don't know, 16th power? And what is I to the, let me zoom out. What is I to the 18th power? So go ahead and try those on your own, and we'll talk about them in a minute. What would I to the 16th power be, and what would I to the 18th power be? Okay. So we're going to look at the remainder table. I to the 16th power. Okay. So the exponent I always bring down, and I divide it by 4 every single time. If I do 16 divided by 4, I'm going to get 4 with a remainder of 0 because there's just no remainder, right? My remainder is 0. So I circle that. I look at my table. Remainder of 0 corresponds to 1. Same thing over here on this side, right? I to the 0 power is 1. So my answer is going to be 1. That's it. Okay. So what's I to the 18th power? 18 divided by 4. What would that be? 18 divided by 4. That would be what remainder what? So how many times can 4 go into 18 without spilling over? 4 times. But I am going to have a remainder of 2. Now, that remainder of 2, that's going to tell me what my answer is. So I look up here, my remainder is 2, so I'm going to have -1. Okay? So those are the powers of I.